Welcome to the Microchip Is podcast. Join your host, Mike Maynard, as he learns about the technologies, products, and people that make microchip technology what it is today.
Welcome to the Microchip Is podcast. Today, I'm finding out what microchip is in the world of atomic clocks. My guest today is David Chandler. David is a senior manager in product marketing for Atomic Systems Clocks. Welcome to the podcast, David.
Thank you, Mike.
So I'm interested. Can you just tell me firstly a little bit about your role at Microchip?
Sure. So as a product line manager for Atomic System Clocks, which are the most stable, commercially available clocks in the world, I'm responsible for a couple of things. One is the long-term strategy of the product line. So that involves working with our engineering team, what we're going to be producing next, what's the next great atomic clock out there. Also responsible for the profit and loss of the product line, working with sales on new business development, and working with operations on forecasting and supply and demand.
That's fantastic. And I'm sure we'll dig into some of those areas in a minute. But before we actually start talking about more of the details, I'm interested because Microchip's got a lot of different timing solutions. So how do the atomic clocks compare to other products in the timing portfolio?
So yeah, that's a great question. Microchip is the only company in the world that manufactures all three of the most common types of stable frequency references, whether they're MEMS oscillators, quartz oscillators, or atomic oscillators. The difference can be broken down into really two broad categories as far as the performance of those products are concerned. The first is like predictable things like accuracy and environmental stability. And the second thing is noise or stability variations due to underlying random processes. So on one end, we have our MEMS products that are probably on the lowest end of the performance spectrum, but they come at a good trade-off of price and size. They're much, much smaller. Kind of have quartz sitting in the middle of that. And then we have our atomic clocks, which are our most stable of all those products.
Okay, so you're looking at real precision timing with atomic clocks, which I think most people would probably have understood. But I guess a lot of people don't understand, exactly what an atomic clock is. So what does the term atomic clock actually mean?
Sure. So there are many different types of atomic clocks, right? But at their core, they all work on this basic principle that you have an electron that is spinning around the outside of an atom. And that electron, you're playing around trying to get it to either absorb or emit energy at certain frequencies. And the entire goal of an atomic clock is just to either create or detect the frequency that's required for those transitions. You can essentially think of it kind of like a bandpass filter, where the properties don't change significantly due to environmental properties. And because of that, it makes an extremely stable reference.
So that's interesting. You're trying to get energy absorbed or emitted at a certain frequency. How does that work? I mean, that sounds incredibly complex.
So, digging a little bit deeper, I think the easiest way to envision this is if you have that electron, you imagine it's kind of like the Earth. It's spinning around the sun, which would be the equivalent of the nucleus. And it's also spinning around our own axis. So, in one case you have the year, the other case you have the day. Because the electron itself is a charged particle, and so is a nucleus, when they spin, they create magnetic fields around them. And as it turns out, when magnetic fields interact, they create states of either higher or lower energy. So when the magnetic fields are opposing each other, it's actually the most relaxed state, or something called the ground state. And what happens is you find the very precise frequency that will cause it to go from spinning in the anti-parallel directions to in the same direction. It's just a little bit of energy. In the case of cesium, you have to fine tune this. It only happens in that very narrow band, which is 9.192631770 hertz. But anyway, you get that spin essentially to flip. So it's now pointing the other direction. And you can think of this as if there was some, giant cosmic beam out there for the Earth that suddenly hit us and caused the Earth to start rotating in other directions, right? So now the sun would rise in the west and it would set in the east. That's a microwave atomic clock, which is what we build today. There are other types. There are optical atomic clocks as well. And with optical atomic clocks, basically you're using light instead of a microwave frequency to cause that transition. And essentially that would be equivalent of saying, hey, the Earth's getting knocked into Mars orbit now or something like that. The big thing is they only happen at these very, very unique frequencies. So you try to get as close as you can to those frequencies, and you start looking at the signal response. And when you find a peak, you can then lock onto that peak.
I mean, that still sounds quite a complex thing to achieve. You talked about cesium atomic clocks, though. Are there different sorts of atomic clocks that Microchip makes?
Yeah, certainly. So we have several different types of atomic clocks, and within those different types, they use different metals. So cesium is one metal, rubidium is a metal. We use hydrogen as well. It's basically everything that has one outer electron. So it's over on the left side of that periodic chart, if you remember that from high school or whenever the last time you had to see it was. But anyway, so we use those different metals, they have different properties and different physics packages to essentially make a very broad performance portfolio of atomic clocks. And these things will change in terms of power, size, cost, but also the performance in terms of stability. So, we start out at the lowest end of our product portfolio for atomic clocks in terms of performance, but it's really neat part called the chip scale atomic clock. It's very low power. It's only about an eighth of a watt. And, we achieve that very low power in small size by keeping everything small so that we don't waste a lot of power or anything else trying to keep it stable. As you increase the size of a physics package, you actually get smaller bandwidth. So that notch filter is essentially collapsing in, right? So as you collapse it in, you have better performance. But when we do collapse in that area where we're manipulating the atoms, or rather, as we make them bigger, you have an issue then where you have to make sure that it's magnetically stable throughout, it's temperature stable throughout. All these things wind up creating more power draw and also obviously a larger size. So, our chip scale atomic clock that runs on about an eighth of a watt using cesium, it's roughly a 1.5 square box, and it'll hold, if I look in a time domain, it'll hold a few microseconds a day when it's operating on its own. So pretty nice stability. But we move from that to our miniature atomic clock, which is actually powered by rubidium in this case. And for that one, it's about 5 watts. It's in a 2-inch square, so not much bigger. It's really a lot more power though. But we get a few hundred nanoseconds. So it's about a 10x improvement in performance. We then have a pretty big jump up to our cesium standards. And these things consume roughly 30 watts. They're about the size of, if you can imagine, a piece of rolling carry-on luggage that you would take on an airport. And those will hold in the single nanosecond range. And then finally, we have our most stable product, which is our hydrogen maser. It's the size of a refrigerator now. You're looking at about 75-watt power consumption, but it'll hold about a few hundred picoseconds a day. So it really explains the variation in the power, the size, and the performance that you're looking at.
And am I right? You also have the devices like the chip scale product at the very small end that will be built onto somebody's board. You also have the system level products as well.
Yes, that's correct. So as I went through that portfolio, the chip scale atomic clock and the miniature atomic clock are devices that you would actually populate onto a printed circuit board, right? Typically, they work in conjunction with an FPGA or a microprocessor or some type of sensor, something like that. Whereas our system clocks, which are, much more stable by about, a factor of 100 or more, those are things that you put in 30-inch rack mount units. So much different types of performance, different customer bases for the different products.
That's fascinating. You've got such a range. And I think if you could explain now what actually needs this accuracy. So where do these atomic clocks actually get used?
Okay. So, it sounds like when you say something like, well, it's only off a microsecond a day, and then this one's off 100 picoseconds, it's really a little mind boggling to us, right? I mean, if you look at something like 100 picoseconds a day accuracy, you're talking about 16 orders of magnitude precision, which is roughly the size of the diameter of an atom to the length of the state of Texas. And that's the precision of our most precise devices. But, as you go through them, so if I start with our chip scale atomic clocks that hold that microsecond a day, they're really for battery applications. You'd be surprised how many applications need this. Anything that's trying to do GPS navigation, If it's worried about losing a GPS signal, believe it or not, the GPS network is nothing more than actually an extremely precise time base that's available to everybody. So, the chip scale atomic clock serves as a time base when you lose GPS. So you can imagine a soldier in the army with it on his backpack would be a battery operation. You can imagine a drone flying around an unmanned aerial vehicle. There's also some unique applications, like they're actually used in seismic sensors in oil exploration on the ocean so that they don't have to continually power those things. They're battery operated. On the other end of the spectrum, I think the easiest everyday idea of what it would be is, as I mentioned, GPS is this precision time network, right? Well, that precise time is being transmitted in the case of GPS from the United States Naval Observatory in America, that is then synchronized with UTC, which is maintained out of BIPM. All those different laboratories all have multiple different cesium standards and masers in them, and we sell to those. So when you look at the time of day on your iPhone clock, ultimately that all has to trace back to our masers and our cesiums that are in those different locations.
That's interesting. I think people would be surprised at the need for such incredible accuracy for GPS, but it's great you're helping us, not get lost. One of the interesting things you mentioned a couple of these applications. What's happening in the trends? Are people demanding more and more of this precision accuracy? Is the market growing?
Yeah, absolutely. So the atomic clock market, we're always struggling to keep up with demand, always investing in new capacity expansions. Some of the reasons why we're seeing such high demand is, if you look at things like 5G networks, they have extremely precise timing requirements because they're transmitting at these extremely high data rates, and they have multiple channels. All those channels and all the timing specifications that you deal with, they basically are to make sure you can handle these high data rates and this huge density of information we're wanting to transport back and forth. So at the core of those networks, you need extremely stable time bases. And so those networks will actually buy cesium standards. Then as you get further out, you'll see that there are some of our miniature atomic clocks also deployed within there. As you move from 5G networks, if you look at something like data center synchronization, a data center has maybe 100,000 servers sitting in this one giant warehouse, and they're trying to act like one big machine, essentially, right? From the outside, you're looking at it as one machine. Maybe it's doing AI calculations or something. All those machines need to be synchronized extremely tightly, right? If they're doing a million transactions per second, well, you're going to need to be able to synchronize them within 1 microsecond, right? So that's another place where you see demand for atomic clocks. Another area where you would see it is radar systems. Radar is essentially just shooting a RF energy out of a radar receiver and getting it back, or maybe it's at different locations where you're receiving it. But again, the time that it takes a signal to go back and forth is really ultimately what determines your precision of the radar. And you really need a very precise atomic clock to be able to synchronize it, particularly if the transmitter and the receiver are located in different locations.
That's amazing. I mean, there's clearly a lot of things driving demand for atomic clocks. I have to ask the question, what does Microchip do really well in the atomic clocks field? I mean, why do people choose Microchip as opposed to other vendors?
We have a lot of claims as microchip atomic clocks. First of all, if you look at Universal Coordinated Time, or UTC, which is the time that's on your cell phone, there's about 80 labs around the world that contribute to this. And then it's all organized at a location called BIPM in Paris. About 70% of the clocks contributing to that. There's maybe 400 total, 480 or something. But anyway, about 70% of them are microchip atomic clocks. So when the people who are maintaining the world's time are using our clocks, it seems a natural assumption that you would want to do that as well. But we are the world's largest producer of atomic clocks. We were the first to introduce the chip scale atomic clock. Our miniature atomic clock is probably the highest selling atomic clock in the world today in terms of just raw volume. So, we are clearly the world leader. And also, we're backed by a major international corporation. Can't tell you how nice it is to have a big corporation like Microchip behind you. And they have a great financial track record. So our customers are really guaranteed the supply is going to be there. You don't have to worry about it being some type of small company that may disappear eventually.
That's awesome. And I mean, you've mentioned the chip scale product. I mean, that's unique, isn't it, as being the smallest atomic clock in the world?
Yeah, so the chip scale atomic clock is actually a really interesting device. You have to excuse the physics nerd in me, but I think, I would use the word cool. Anyway, if you look at it, the physics package, which is where we actually manipulate the atoms inside the chip scale atomic clock, that whole area is smaller than a sugar cube. And actually, when we talk about calling it chip scale, it's because the area where we actually keep the gas, the cesium gas, is manufactured using IC manufacturing technologies. So it's really amazing how small we got it. And then the gas cell and what we call the rest of the physics package, so things like the heaters, the laser that queries it, they're all inside this evacuated area so that we use very low power. So it's not just really small, it's also you're taking something that 20, 30 years ago, you'd be looking at, gosh, I need 10 watts, 15, 20 watts. We're now down at an eighth of a watt. So it's really fascinating technology. It's really cool to see it actually being built.
That's awesome. And does that or any of the other technologies give rise to like any unusual application? I mean, everybody likes to hear about the crazy applications or the surprising applications.
Yeah, so some of the most interesting applications I think I've seen, we can actually measure gravity with atomic clocks. Turns out, due to general relativity, Einstein proposed however long ago, I guess back in the 1930s, turns out that as gravity decreases, time actually travels more rapidly. It's not just a measurement problem, it's truly like the clock will behave differently. You experience time differently in different places, right? So if you took, and I've seen this, right? People will take an atomic clock, particularly the cesium standards, which, they can transport in a vehicle. They can take it from the, sea level up to the tip of a mountain and then bring it back down. And you'll see that there's more elapsed time on the one that was going up the mountain than one that maybe stayed at sea level the whole time. So that's really fascinating. And actually, that exact problem is why just a few weeks ago, there was a memo issued by the White House about we need a lunar timescale because the gravity on the moon is so much less than that on Earth. As we start exploring the moon again, we're going to need to have a time base on the moon. If we were trying to coordinate the moon between Earth's surface and the moon, we'd be off by as much as 56 microseconds a day, which doesn't maybe sound like a lot, but if you think of a 56 microsecond error for a GPS satellite, that's 10 miles off. I mean, it's a huge number. So that's why the moon is going to need its own time base and actually its own positioning systems too. And all those are going to need atomic clocks, just like we have today on Earth.
That's incredible and blown my mind that such a small error can result in such a big measurement error from GPS. So I think it really brings home how important the accuracy of these clocks are. I mean, people will have heard about atomic clocks, maybe not really understand them. I mean, do you come across any common kind of misunderstandings about atomic clocks?
Yeah, there are actually a couple that are propagated out pretty frequently. If you just Google atomic clocks and try to read how they work and stuff, you'll see a lot of times people say, hey, an atomic clock is this way because the atom is actually physically vibrating at this frequency. That's not really what's going on. What's going on is we're finding the frequency of the energy required to get the electron to jump from one state to the other. So the atom itself isn't sitting there moving at that frequency. That's one misconception. Another big misconception I run into people is they hear the word atomic and they immediately think, oh, that must be radioactive. They associate it with other things that have atomic in front of them, like atomic energy and things like that. Just to be clear, that's not the case of what's happening with atomic clocks at all. There is no radioactivity related to the actual transition processes or anything like that. Atomic processes like fusion or fission involve losing or gaining protons or electrons. Or sorry, protons or neutrons, I meant to say. We're not doing anything like that. All we're doing is moving kind of the state of electron within an atom. So very different, fundamentally different process that is not radioactive at all.
That's reassuring to know, David. I'd like to switch tack a bit. I mean, one of the challenges must be you're working in this very specialist field of atomic clocks, but you're part of Microchip, which, although it's very broad, and this podcast is showing me that Microchip, has a huge range of areas of business. it's still thought of, I think, as a microcontroller company. So how do you fit with the rest of the portfolio?
So that's an interesting question. Basically, if you look at it, people think microchips, they think microprocessors, but there's a huge part of the company that really is doing other things, right? We're really a diverse electronics company. We serve multiple markets and produce all kinds of different products. Our embedded atomic clocks, so things like our chip scale atomic clock and our miniature atomic clock, actually are used frequently to time or a microprocessor or an FPGA. If those are being used in things like precision sensor applications and things like that, they'll need the precision time of an atomic clock. So that's one way we dovetail in with the portfolio. It's also just lots of other areas that customers who are buying microprocessors, maybe not for a consumer electronic application, but many of the other industrial, aerospace and defense data centers, they're also the same customers who need atomic clocks as well.
So you obviously work quite closely with other business units at times, producing solutions that use atomic clocks and other microchip products.
Yes, we do. We work with the FPGA group in kind of a symbiotic relationship, right? They need it for certain applications, like particularly space applications. They need precision timing that are going into things, combined with maybe the Polar Fire RT FPGA, which is specifically designed to operate up in space. And we have a space CSEC that is also manufactured for low Earth orbit. And, we talk closely about how these things should be interacting. Another group we work closely with is the timing component groups. They make these very precise frequency synthesizers that can give you all different types of frequencies. And what's interesting there is we actually use their synthesizers in our products. So we do work very closely with a number of different groups within Microchip.
David, this has been fascinating. I feel I've got so much to learn about atomic clocks, but it's been a great introduction. There's a couple of things we like to ask people before we let them go on the podcast. So the first is there any engineering advice that you can give listeners, perhaps something around using atomic clocks?
Yeah, absolutely. Biggest thing I would tell an engineer is don't make your timing an afterthought. It can have huge impacts on your design. There's people who assume they're just going to be able to get away with an onboard oscillator or something on, when we have some of these embedded, and then they find out they're 3 orders of magnitude off in precision, and suddenly it's an emergency. On the flip side, there are people who will come to us and say, hey, I really want this atomic clock. And, we need to say, hey, look at your budget, look at your price and your performance. You may be able to use one of our MEMS oscillators, could be the correct solution there. So it's very important to understand your timing requirements and the budget implications around that.
That's awesome. I think that's great advice on both sides. So think about it, but you don't necessarily always need that atomic clock accuracy. In terms of summarizing, is there one thing that you'd like to pick out that you'd like listeners to remember about your atomic clock products?
Yeah. I would basically say that our cesium standards are used to define the unit second that we all know today. And they require no calibration for the life of the unit at all, right? So it runs for 5 years and you have the definition of a second sitting there on your desk. So if you need an absolute source of time or frequency, we can provide it. The other thing I would say is that we have this huge portfolio. So we really are a one-stop shop for any timing reference you would need.
That's great. Thanks so much, David, for your time. I really appreciate it. It feels like there's probably going to be lots of questions. if listeners would like to get in contact with you, what would be the best way?
The easiest way is probably to just send me an email. My email is david.chandler@microchip.com. There's other ways of getting in touch with me through the website, but that's probably the most direct way. Just send me an email. I look forward to any questions and would be happy to answer them.
That's awesome. David, thank you so much for your time and explain to me what Microchip is in the world of atomic clocks.
Thank you, Mike.
Thanks for listening to the Microchip Is podcast. Please follow us on your favorite podcast platform to keep learning about the many technologies, products, and people that make Microchip what it is today. Look out for our upcoming Microchip Is podcasts and our new Beyond the Microchip podcast series.